can actually work on the challenges that we're going to give you at the end of this tutorial. All right, so today we're going to be working with sensors in Webots. And just like normal robots, we can attach sensors onto each of these robots. And we can actually see a list of all of the sensors on this robot right here. If we go to the scene tree on this side, and we hit the drop-down menu to the left, and then we go to the turret slot and the ground sensor slot. So these right here are just basically a collection of all of the sensors that are attached on the robot. So we have a GPS, gyro, 2 light sensors, and a camera sensor. And there's actually more to this robot, and you can actually find that in the documentation. So if we go back here, support and assistance, and you go to this Webots documents website, you can actually find this robot section. And then since we're using an epoch, you can see over here, it's called an epoch. Then you will see there's a section for epoch, and it will list some of the distance sensors. It'll list all the distance sensors that it has. And also, if you go back to this GitHub page right here, you scroll down and you click on this link right here, then it'll pull up a nice diagram of the main camera sensor and 8 IR sensors that it has. So between this diagram right here and the scene tree in Webots, it'll give you a good overview about all the sensors attached to this robot. Right. So now to actually get to the coding part. Each sensor, if you want to code and probe each sensor, the code is pretty much identical for each specific sensor. If I pull up this code right here, this is a sample code for getting the gyro, but I'm going to use it more of a template. So the first component of working with sensors is your pound include statement, which is right here. And since it's a gyro sensor, I'm just going to pound include gyro.hpp. So that's the first component, our pound include. Then, just like with our robot, we have to create a pointer to our sensor class. So we have a pointer called gyro, and then this is the syntax just to instantiate it. So that's component number 2 right here, creating my gyro pointer. Then step 3 would just be enable the gyro. So you just use your pointer, call enable, and you pass it the time step. And we worked with time step in the previous session, which was yesterday. Okay, now that you have it enabled, part 4 is just getting the values. So you can use your pointer, and every sensor will have a get value or get values method associated with it. So you can just use your pointer and call get values. And now gyro, the gyro's get values actually returns an array. So this is why we indexed it using 1. And each sensor works a tiny bit differently with its get values return value, but you can see all the information you need inside your Webots documentation. So remember from yesterday, we can go into documentation, go to reference manual, and then we go to nodes and API functions. And you scroll all the way down to, let's say, gyro. Here we go. It'll give you all the information you need about this particular sensor. So you can see here, list the enable method, and all the get values information is all right here. So whenever you have any doubts about a sensor, you can go to this documentation and it'll give you a good overview. So as a brief recap, for every sensor, the basic components you need are pound include, instantiating a pointer, enabling your sensor, and then you can do your get values from there. So now Victor is going to go through the specifics of each sensor that you will encounter in the RoboCup Junior Rescue Maze competition. So Victor?
All right. I'm first going to go over the distance sensors, gyro, GPS, and light sensor. And we're going to save the camera for later because it's a bit more complicated. But as Jeffrey said, you first need all your include statements for whatever respective sensor you're planning on using. So we're first going to talk about the distance sensors. So here's my include statement for the distance sensor. And the distance sensors on this particular robot, the epoch, are infrared distance sensors. So since there's 8, I'm actually going to create an array of pointers to the 8 proximity sensors. Now, ignoring all the gyro and other sensors for right now, um, the way we're going to initialize these 8 sensors, normally we just have to have a single sensor and get it and enable it. Well, since we have 8 sensors, we need a good way to enable all of them. And to do that, I have just constructed a for loop that loops 8 times. And how it works is pretty much um, for the array of infrared sensors, I get the index I, and that equals the robot get distance sensor and PS plus the postfix of the sensor number. So I, in this case, would be 0 through 7. I just convert that to a string. And all the distance sensors are called PS0, PS1, and so on. So I just set that pointer to whatever sensor it is. And then right after that, I enable it with the time step. So that's going to initialize all 8 of your distance sensors nice and easy. And the way you use your distance sensors, as Jeffrey said, it usually follows the same format for each sensor, but there's a couple of things we need to clarify about how these sensors work. So first of all, if I pull up the epoch documentation page, you'll see we have this picture once again that describes where each sensor is pointing. So PS0 is pointing this way, PS1 is pointing that way. What's important is how you interpret the sensor values you get back from reading the sensors. So if you look at this graph right here, this is called a lookup table. And what a lookup table does is it maps the distance values inside of the simulation world to the perceived sensor readings. So if you'll notice, this is actually a very close range proximity sensor because of it maps it between 0 and 4095. The closer you get to the sensor, the higher the number goes, up to a max of 4095. And the further away you get, the closer it gets to 0. You'll notice that these units are in meters, so actually it's a very close range distance sensor. All right, so if I were to run my current sample program, all that's going to do right now is print 4 out of the 8 distance sensors by calling a get value for whatever index sensor I'm getting. So if I build that and then make sure it's attached right here. So right now our robot 1 has the sensor sample attached to it. If I run the program, it's going to just repeatedly print out the values of my proximity sensors. And you'll notice for the most part, they're all pretty low right now. But if I move closer to a wall, and if I rotate it slightly, sensor 0 is starting to increase to around 200. And you'll notice it's already pretty close to a wall because, once again, this is a very close range proximity sensor. And once I get really close, it goes up to into the thousands, like 2000. So that's the idea of how you use the proximity sensors. Next, we're going to go over the gyro. So the gyro, if you ever used a gyro in NXT or EV3 robots, you normally expect the sensor to give you back your angle heading. But gyros and Webots actually model real-life gyros and how they work. in that they actually give you back angular velocity, and you have to calculate your angle heading yourself. So once again, we create a gyro, and the way that we're going to calculate our angle heading is using a couple of functions right here. First, we have an update gyro function. Additionally, we have a get angle. So the update gyro function, since we're getting angular velocity, we're going to have to use a little bit of calculus concepts in order to find our angle heading, in that we're going to integrate our angular velocity to find our angle heading by multiplying the current angular velocity by the time step and adding that onto our angle. So if you haven't taken calculus, that's perfectly fine. This is just pretty much how we turn our angular velocity into angle heading. And we're going to need to call this function every single time we loop. Down here, this get angle function just converts the angle from radians into degrees. And radians is the default unit of our gyro. It's just easier to work in degrees. So I'm going to comment that out. And down here, I'm going to need to do two things. One thing is I'm going to have to update gyro each time in my while loop. And the second thing, I'm just going to print out the angular velocity as well as the angle heading from my get angle function. So the angular velocity is given by the gyro on 3 axes, the x, y, and z axes. We only care about the y-axis, which is pretty much the yaw of the robot, because it's really not supposed to rotate around the x or z axes. So y-axis, x, y, z, that's just index 1. So if I build that and I run it, you'll see it starts printing out angular velocity and angle heading. So if I move and I start turning the robot, oh, actually, we're not updating our angle. And sorry, Webots is really slow right now. Okay. One second. Let me come back to the angle because it was not updating the angle. I'll find that out as Jeffrey speaks about the camera, and I'll come back to you guys about that. But right now, let me go over the other sensors, and then I'll come back to you about the angle. So we also have a GPS sensor. This GPS sensor is just responsible for giving you the X, Y, and Z coordinates of your robot. And once again, it's the exact same syntax as all the other sensors. This XYZ coordinate is relative to the world origin. And right here, we just have a simple print statement to print out all the GPS values. So this is the exact same coordinates you'll find under your robot1 transform in this translation field. So all you have to do to get your position is first call GPS get values and then index it appropriately for what you want. So it's going to return a pointer to 3 values. You can just index it like an array. So index 0 is x, index 1 is y, index z is 2. Sorry, I said that wrong. For the second one, which is y, that's just index 1. If we run that, we just get our position. And you'll notice that it rounds this value, the translation, down here. All right, wait for this to reset. Actually, let me restart Webots. All right, sorry about that. It's not normally that slow. But finally, we have a heat sensor. So there's two heat sensors on this robot that we're actually simulating heat using light sources because Webots doesn't have heat sensors by default, but we're going to use light sources and light sensors in order to do that. So first of all, you're going to create these two heat sensors by doing get left heat sensor and right heat sensor. And these are added onto the robot, not on the default base robot, but these were added by ourselves through the world. So this is the name you're going to have to use to get the heat sensors. You actually won't find these sensors in the documentation because they're not there by default. And all we have to do is, once again, get value these two sensors. And it's made to mimic temperature in Celsius. So the ambient temperature of the world is going to be around 20 to 25 degrees Celsius, while standing next to a heat victim is going to be around 37 degrees Celsius. And let me open a world with a heat sensor in it to show you guys. Open world, advanced. All right, so you'll notice that there's a heat sensor right over here, and it's emitting what looks to be like a red glow. That's the light source. So our heat sensors are going to have to pick up that light source. And if I open the text editor, all right, and down here, build that. And then robot one, remember to attach the controller. Okay, so if I run this, it's going to report the heat of the left and the right sensors. You'll notice that it's approximately around room temperature. If I move this robot next to the heat sensor, the heat source, depending on the position of the heat sensor, we should see it start to increase. And you generally have to get pretty close in order for this to demonstrate 37 degrees Celsius. And actually, this might be an old world. Also, let me come back and see if I can go back to my old world and get the heat victim. So right now, while I do that, Jeffrey's going to go over the camera sensors, and I'll come back to you guys on that.
Okay, so I'm going to start talking about the camera sensor. So in Webots, there's actually two ways you can use the camera. One is just like a regular camera sensor. You grab a matrix that represents the image that your camera sees. So each element represents a pixel of the image. Each element is an RGB representation of each pixel in the image. And that's a little bit more advanced because you actually have to do image processing. And that is actually an element of this competition. We're actually going to go over that in tomorrow's session. For today, we're going to talk about recognition colors. And the way recognition colors works is I can take objects inside this maze, for example, this wall, and I can associate a recognition color to that wall. And this recognition color has absolutely nothing to do with the actual color of this wall. So even though this wall is like light blue, I can assign it a recognition color of like black, and it won't affect the appearance of this wall. It acts as a sort of tag. So when this wall comes into view of my camera can recognize it as, hey, that object has a recognition color, and that object recognition color is black. And we can use this recognition color to recognize objects around the world. And what the RoboCup Junior team has done is they've taken these visual victims placed around the world, and they've assigned recognition colors to it. So as your robot moves around the maze, if your camera spots one of these victims, it will return saying, hey, I've seen an object that has a recognition color. Maybe it's of interest. And their recognition color for this world is actually 111, which would just be a white. So to actually go through and find these recognition colors, we're going to have to start off by, as with all sensors, we need to pound include camera.hpp. Then, just like with other sensors, we have to initialize a pointer to the camera using this syntax. And then we have to enable our camera. And now we're not going to do a standard enable as we did with the other sensors, but we're going to do a recognition enable. If I did a regular enable right here, that would mean I'm using my camera as a regular camera sensor and grab a matrix of all the pixels. But we want a recognition enable. I'm going to pass the time step just as normal. Then we can use our camera pointer and we can call this method called get recognition number of objects. And what this does is when your camera is looking on at the maze, it could see a lot of objects that have recognition colors. It could see a wall, the floor, a victim. It could see a whole bunch of things. What this does is it returns the number of objects that it sees that it has recognition colors. So if there's a wall that has a recognition color, a victim that has a recognition color, and that's it, it will return 2 because it only sees 2 objects with recognition colors. Then what get recognition objects does is it gets a pointer to a list of all the objects with recognition colors. So object is a pointer to a whole bunch of camera recognition objects. Then all we have to do is iterate through this list of objects that we see that have potential to be that have potential to be victims, right? And remember, victims need to have the 111 recognition color on it. So that's literally what we're going to do. We're going to do for I is less than num objects. So for each object inside this list, we're going to check if objects I, remember this is element I of the objects, dot colors, this returns the recognition color of the object that we're currently looking at. And then we're going to compare it against victim color. And victim color, again, is just the 111 that we're looking for. And array equals is a very simple function that we wrote. It just tests equality between 2 arrays. So for each object inside this list of objects, we're going to do a dot colors, which gets its recognition color, and then we're going to test it to see, hey, is this a victim or not? Then if the 2 arrays prove to be equal, that means it is in fact a victim. And then we're going to print out C victim. Then you can actually go even further and you can grab the victim's position relative to your object, relative to your robot. So we can actually do objects I, because over here we realize that objects I has to be a victim, because objects I's recognition color match the victim color that we're looking for. So object I now represents our victim. So we can do object I dot position, and that returns the position of the victim relative to our robot. And then all we did here was just print out the coordinates of the object relative to our robot. And if any of this confuses you at all, make sure you do read the documentation on the camera. Remember, you just go to documentation, reference manual, and the camera section. And this will give you all the information that you will need for working with the camera. And I highly suggest you do read it again. So that's basically all this does. It just tests if it sees any victims, and then if it does, it prints out the object's position relative to the robot. So now we're going to see this code in action. So once again, remember, as always, build your code. Build, we can just hit cancel on this. And now double check that for your epoch that you're going to use, I'm going to use the one on the right, that its controller field is marked as the controller that you want to use. And I'm using camera.cpp. So right here should go camera. Now all you have to do is hit run. Okay, now as I move my robot around, you will see that it detects this victim right here, right? Because it's in the camera's view, it's right in front of it. And this right here is the position of the robot, of the victim relative to the robot, right? So if I can move it closer, you will see that this number drops, or this number increases. If I move this farther away, this number decreases farther into the negatives. And I can also move it left and right, and this first value changes accordingly. So then, once you have this coordinate, it should be pretty easy to triangulate and go next to this victim and go get it, which we will talk about in tomorrow's video. All right, okay, so I'm gonna give a little time for all that to set in, and then we're gonna move on to the next topic. Okay, so as you guys see, there are various panels on the ground of the maze. Like you have this gray tile right here, which is a checkpoint. You have this orangish tile, which is a swamp, and then you have this pit, which is black. All right, and as we go around the maze, we're going to need ways to figure out what color is the ground beneath us, and that's why we have a camera sensor that acts as a color sensor. Right, and you can see it by this. It's called color sensor with a U, because the people who made this are British. And basically what we can do is, instead of initializing it as a recognition enable, what we're gonna do is, just like before, we're gonna make a pointer, and now this is actually my color camera, because this sensor actually points straight down from the robot. So if you envision like a color sensor you would use for basic line tracing, it's just a camera that points straight down at the ground. Then we're going to instantiate this camera with the exact same syntax, except with this name. Then we're going to enable it using a regular enable, not a recognition enable, but a regular enable. Then what we can do is we can do our color and do a get image. And now this camera is peculiar in the fact that it only has one pixel. And that may seem kind of weird, because whenever you think of images, it has thousands and thousands and thousands of pixels. So it gives you a clear image. But with this color sensor, as with all color sensors, you're only interested in the color that's right below your robot. You're not interested in piecing together an image, right? So for this camera, we only need 1 pixel to grab the color that's right below us. And then what we can do is we can do a color cam get image, and this will return 1 pixel that has 4 bytes RGB and then something else, but we're only really concerned with the RGB for now. But then you can use that RGB to tell the color of the floor beneath you. And to get into specifics, I highly recommend you read the documentation so you can see the get image function is laid out right here, and it has a lot of good information. And as one of our many challenges that we're going to propose to you, you're going to work with this get image function, and you are going to figure out what colors, what's the range of colors that you'll look for to identify gray, orange, and black. Right? So you're going to use this pointer that this get image returns, and then you're going to try and classify the ground beneath you. So that's kind of it for camera. Once again, if you're confused, I highly recommend you read over this documentation again, or we have videos on YouTube that you can watch over again. So yeah, without further ado, I guess Victor is going to talk about mini challenges or show you some new code. So, Victor?
All right, so sorry about that. I think the world we uploaded to GitHub had a slight problem in the way that we set up the sensors. So we're gonna re-upload that in right after this. But just to show you guys the proof of concept, at least for the the heat sensors and the gyro, we have this other world you'll see, and this is a different rescue maze that's available on the rescue maze GitHub. So first of all, let me print out the value of the heat sensor. So right now, it's printing out something like ambient temperature. So once again, if we move the robot and we rotate it, it's going to go up to around 37 degrees, which is pretty much body temperature. So once we edit the world, we're going to push it to GitHub as soon as possible for you guys. And another thing is that for the gyro, and we're going to let the program build. And all right, so if we run that, all right, so this is our angular velocity, and this is our current angle heading. So the one thing is that actually rotating the robot within the world, this is something I forgot about a while ago, doesn't actually change the angular velocity. But there is something you can do. You can apply a force to an object by hitting left alt and then clicking and dragging on the object. And as long as simulation is running, all right. All right. Sorry, my simulation is kind of slow. Okay, well, the idea is that, of course, the robot spun out of control. The angle heading is going to change as a result of integrating the angular velocity. So your angle heading will change if your motors move or you apply a force to the robot using the Alt key. But other than that, actually rotating the robot within the world will not make the angle heading change. So as soon as we end this meeting, we'll update the world for the heat victim. Besides that, for the next meeting, we're going to go over how to improve victim recognition using OpenCV and how to connect Webots to your OpenCV external libraries. So one thing is that before that meeting, installing OpenCV usually takes some time. So be sure that you, first of all, make sure that OpenCV is installed correctly on your computer and it's configured within your, if you're using Windows, within your like path. So at their OpenCV website, you can see a list of releases. So just download the latest one for whatever system you have and just verify it's working. And that's going to ease up a lot of problems we may have tomorrow when we try using OpenCV for reading in the camera and performing image processing on the camera. So besides that, that's about it.
Okay, so it's about time, but I just want to do a last wrap up and just a reminder. I'm going to share the screen here. Okay, now everybody, just a reminder that I hope that someone in here, in this audience, will actually go try out the mini challenge. Doesn't matter, it's a day 1 or day 2, and then go on this website right here again. Then I'm going to show you how to get there in case that you forgot how to get there. I'm going to copy that in the chat window as well shortly. And so you go to the website, everything is there from day 1 to even the future agenda. Then the shared your code, and this is where you're going to upload your code. It's very simple. You just upload your CPP file, and then we try our best and always list the best 3 solutions, and we give out recognition online as well, and certificate and all. And then if you want to look further down, then for the agenda, the mini challenge, like what Victor just mentioned, in case that you lost the link, you don't know where you get to the link to find the access to challenge, is always here. Now, very quickly, now the OpenCV website, now this is tomorrow, and I also provide a link there where you're going to upload or download rather install the OpenCV as well. Okay, so all the links are here, and the documentation again, which I mentioned yesterday, is also they're all here. All the great links that is useful for you, they'll be all here. Now, if you have technical questions, again, post the technical questions at the Discord, and then if you want a fast response. If you have any questions, particularly for your Robot C, I kept saying Robot C, regarding the RCJ maze in the coming September, they will be at this forum. Okay. Now, in case again, if you forgot that this site, no worry. Always start from the RoboCup Junior website, which I'm 100% sure everybody here is very familiar with. Start from that website, you go to Rescue, Simulation League, and then from there, then you find the Rescue Maze, and then go to find the C and C++ tutorials, and voila, you come back to this site again, okay? So as long as that you know where to find the information, all right? Thank you for attending. So be tomorrow again at 8 o'clock. We will see you again. Or if anyone has questions, please feel free, speak up and let us know what your questions has. Otherwise, then have a good night.